Okay, so good morning everybody. As presented before, I'm Peter Svensson from Trondheim, and I'm going to talk about a special type of room, usually a small room, which is rooms used for video conferencing. So first I will start with talking about why the video conference room is a situation which doesn't follow classical room acoustic conditions or theory. And the hint is, of course, that we have two rooms involved, not one room. But it's not the same as the classical coupled room situation. Then I will, in spite of what Erling Nilsson just presented, I will use diffuse field-based theory as a simple model, as a first model. That could be extended to more advanced models as well. I will present results from a simple listening test that we did, which just confirms what we know, that it's very worthwhile suppressing reverberation by different means. Then the tricky aspect of what should be suitable recommendations for reverberation times and or other parameters in video conference rooms. I have used the input from a PhD student, Hassan Sidan, a master student, Erling Gundersen, and colleague researchers Ulrich Reiter and Tone Bergin in this presentation. So I should use this one. So a video conference situation which could be illustrated like this. Such a situation is in a way such that the room, both rooms, need to fulfill three tasks at once. Very often we have more people in each room, and that means that it needs to be a decent meeting room. In the situation here with a single person, it's not like that. But the room also needs to be a recording room because we are picking up the sound by microphones, and it's a sound reproduction room. It's a listening room. And we know that even though we cannot immediately perhaps grasp what is the difference between these, but we can probably realize that a meeting room could typically benefit from a little bit more reverberation than a recording room or a listening room. So again, a little bit of a recapitulation of what Erling showed before. We see the classical basic relationships. For instance, this one showing that the sound pressure level has the direct sound and the reverberation part with Barron's suggested range-dependent amplitude. Here I have inserted directivity factors for the source and the receiver, because in this situation we have a source which could be a talker or a loudspeaker, and we have a microphone which can be not a measurement microphone but actually a directional microphone. So we need to take both of those directivities into account. Then, exactly like Erling showed, we can estimate the C50 based on this diffuse field theory, and with Barron's addition, I think we get a little bit of a better estimate than if we use classical diffuse field theory. This illustration here is just a picture of an impulse response, and this tries to show that the model here corresponds to that we have a distinct direct sound and more or less diffuse reverberation following. So this can be discussed apparently, according to what Erling said, that in some rooms we don't have such a clear relationship between C50 and T60 probably, but still there is such a clear relationship usually that the C50 has in a way little additional value. Again, in special situations it will have added value, and in particular here where we have a direct sound which can be modified in amplitude quite much by using directional loudspeakers or microphones. So then the two-room acoustics versus coupled rooms. Coupled rooms means that we have some opening between a source and the receiver room, and there will be sound transmission both ways. In a video conference situation, we have a microphone here and a loudspeaker there. The sound is fed one way. It is certainly so that the communication is two ways, but the feedback of this sound back to the source room is usually suppressed very efficiently by echo cancellation systems. If it hadn't been, it would be we get very annoyed by acoustic feedback in video conferencing. So we can view the situation as a one-way transmission. Then, if we do that, if we view the transmission as one way, what we get for the transmission from the speaker to the listener is a convolution of two impulse responses. And if we use this simplified model with a direct sound and an exponential decay, the result of this convolving two such impulse responses is that we get one direct sound and we get two exponential reverberation tails that are added together, so we can both see them, one for each T60 in the two rooms. And most importantly, we get one non-exponential reverberation part, which happens when you convolve two exponential parts. This part can be suppressed so that we get a more classical situation. If, for instance, the microphone is very directional or very close to the mouth, like here, or the listener wears headphones, because then the second room is, so to say, not involved at all, or if the listener here sits very close to the loudspeakers. For instance, if you have a personal Skype meeting, you're sitting close to your laptop, then you have a simpler situation. But all of you have probably been in classical video conference meetings where you sit around a larger table, and we get a situation like that. So what is the implication of that? Well, we will see first with some measured examples. It was in a master thesis by a student, Ellen Gundersen. He measured impulse responses in 11 rooms that are used for video conferencing. And they ranged from quite dry to quite reverberant. I would say surprisingly reverberant for a video conference room. So it's not a completely even distribution of cases. Most of them are very dry, between 0.18 and 0.34 for EDT averaged in the room. And C50 also averaged over some measurement positions. If we plot the C50 and EDT against each other, we see quite a clear trend. Then he did a simple simulation of a video conferencing situation by convolving the measured impulse response with itself. That would more or less correspond to that we have a video conference with two identical rooms involved, the same distances in the source and the receiver room. It's not a really great attempt of simulating the situation, because it would mean that we assume that the directivity of the source here and here is the same, and the directivity of the microphone and the directivity of a human listener is the same. It's not completely great, but we can get an idea of what happens, and when we do it, of course, the C50 will get lowered, and the apparent reverberation time will get longer. So these arrows show that these three cases, when we convolve them with itself, it's moved to up here. This one is moved up here. So we can see that he found that on average the C50 was lowered by 7 decibels. The early decay time prolonged by 56% on average for these 11 cases. So this shows that when we have this convolution, it's really worsening the conditions, obviously. A little theory about what I hinted at before, that we get a direct, when we convolve those impulse responses, we get a direct sound, we get one exponential decay with the reverberation time in room 1, another one with a reverberation time in room 2, and then the non-exponential part, which can be written as a difference between those two. Just as a numerical example of of what that can lead to is that if we just take two rooms and we insert some realistic numbers, and then we compare a case where we have a microphone at the short distance and the directional microphone, then we can get a decay with the direct sound and the decay which is quite close to exponential. If we have longer distances, not so directional microphones, we can see this non-exponential decay. And the important observation there is that in this situation, we miss or lack important early energy. The energy is kind of pushed back to later times. So a third little part of this presentation is a small listening test that we did, where we did not study a complete video conferencing situation, but we studied different recording situations in the source room. So we had a room where we could change the reverberation time or the absorption. We changed the microphone distance, we changed the microphone directivity, and then simply listened to the speech reproduced over a loudspeaker and asked people to rate or to state what they preferred. We used a special type of microphone so that we could use, I wrote a hypercardioid microphone here, but it's actually a third order hypercardioid microphone. Some of you might know that there's a microphone called an Eigenmic, which is a little spherical microphone, very expensive, very beautiful, with 32 microphone elements, which you can set to be an omnidirectional microphone, cardioid microphone, third order cardioid microphone, etc. So it's very good for such comparisons. We tried two different distances, we had two different reverberation times, and asked for preference. And then these, we had 12 different cases then, and the preference plotted against the estimated C50 value. This is estimated based on this diffuse field theory. So we can see that when we have such a huge range of C50, up to 20 decibels, down to 2 decibels, then certainly the C50 is a very good predictor of preference. And we can reach high values if we manage to use directional microphones in a reverberation in a video conference. So then, to come towards the end, if this boils down to the very basic question of, since many standards do after all specify or recommend reverberation times, if we look in the Norwegian standard with recommended acoustical conditions for different types of rooms, the closest that we come is what's called classrooms and meeting rooms. And the classifications are A is excellent, and then with good and minimum requirement. These, based on what we saw in making measurements and convolving impulse responses to simulate that we connect two such rooms together, it seems like maybe we'll need to scale these values down by 50-60%, which is a bit extreme, or which would be a bit extreme, because that would give too short reverberation time for many situations. So we would either have to do it so probably that we should adjust these values a little bit further down, but we would probably also need other parameters than T60, like Erling discussed earlier. So if we would just scale down values by say 30% based on those simulations, we could use another very pragmatic approach, saying that what is considered as a classroom class A would be quite similar to a video conference room class B or something like that. This is just a first kind of discussion about the situation of video conferencing. So I think that more experiments would be needed. A little bit like Erling said, that when we do an initial study, we can identify situations that need to be studied further. So to round this off, I try to point out that the two-room situation requires slightly modified room acoustical models. Video conference rooms probably, after all, do need to be more absorbing than ordinary meeting rooms, but not too absorbing, because that would not give a pleasant meeting room. Directional microphones will certainly help, but then we have this slightly tricky situation that the room must be specified by itself, but in addition, the video conferencing equipment has to be specified separately from the room. We can open up for lots of discussions saying that these simple models are too simple. Early reflections will be important. Coloration effects can happen when you have a microphone picking up the sound, etc., etc. But we do. I think that this situation of video conferencing room is a case which will probably be more and more used. So we need to. So I would urge more of you to try to think more about the video conferencing room and discuss how we should specify the criteria for that. So that's all for me. Thank you very much.
Two short questions. If you have any questions. Okay, Jack first. What's Adrian first? Okay.
Oh, no, I don't know.
You just scratch. Okay, yeah.
You reverted to criteria in terms of reverberation time, rather than said we may need other parameters.
Yeah.
There was no discussion of room size, and if you had clarity, that would be helpful. Maybe even rather than reverberation.
Yeah, it's I kind of scratched on the surface, but and not taking the full step of. Once we start to discuss C50, we probably also need to include the video conference equipment, because the so this situation here affecting the early part very much will be very dependent on directivity factors. So so in a way, we have a minimum requirement, which would be the reverberation time, I think, for the room, to specify the room. In addition to that, we need specifications of the video conferencing equipment, which is then the combination of the room and the electroacoustic installation, which is sometimes permanent and other times not permanent.
You've also got assumptions then about distance, that are as significant as the directivity factors.
Yes.
Once you're making those assumptions.
Yeah. So that is part of the same problem, that we need microphone, electroacoustic system and distances, in addition to the basic room itself. But the basic room itself should certainly not. We would prefer that it doesn't have a reverberation time of 0.9 or even 0.6. Because I think that many video conferencing rooms are placed in an available meeting room in many buildings. I'm not sure if I answered your question. I think that it's a more complex case that need more factors, even when using the simple diffuse field model.
Okay.
I see you're using early decay time there, the descriptor, rather than T20 or T30, obviously because you're interested in what's happening at the top of the decay immediately after. But if we're trying somehow to think of decay time in any form and C50, just conceptually, doesn't this give us a problem? Because in a room with half-second reverberation time, we're looking at a very, very small amount of the decay, probably something around about T3, somewhere between T3 or T5. Or if you like, by the time 50 milliseconds has occurred, by the time the cutoff point of your C50 happens, the sound's only decayed by about 6 dB. So why should we be bothering even to think about classical acoustic theory in here? Why start by thinking, well, we'll use a descriptor, a classical descriptor, to try to work with this, because it clearly isn't working.
The classical model is needed to try to do a first attempt of a simplified analysis, which will tell us that this happens. So that this convolution of exponential decays will smear out and give us a longer reverberation time effectively.
Yes, but sorry, misunderstood, but when you're looking at the decay, you're then seriously, you're looking at something which is happening much further down the decay time than actually affects the speech clarity. Did you not? You should we not really be looking at what's happening in the first 5 dB of the decay?
But we are looking at the C50, and that is related to the speech. That is the speech clarity measure, after all.
Yes.
So maybe could we discuss this further, perhaps? I'm maybe not getting the
I think
question.
I may have misunderstood your method, but yeah, I think we can discuss it.
Okay, thanks.
One last question here.
I have a question to the previous slide showing dependence of C20 versus EDT.
In the measurements,
This one. So both of these parameters are point-dependent parameters.
yeah.
That means that they differ dramatically in the room. Therefore, both of them are accompanied by a quite large
Range variation.
statistical distribution.
Yeah.
And therefore, instead of this, say, line,
Hmm.
we should have rather quite a... Yeah.
Something like this.
Yes.
Yes.
Could you comment this?
Yeah. So these are averaged. That off the top of my head, I don't remember the number of positions that were averaged here, but there's averaging of a few positions for each point here. But it doesn't illustrate the range, which is absolutely true that it could be it would be very useful.
And in the reverberant room, this width of this sphere is quite large in both directions. EDT and in the C50 direction. So it takes quite large part of the whole picture.
It does, even though if we had looked at a smaller range here, then it would be all those details would kind of disappear in the big ribbon. But here, when we have such a relatively large distribution of cases, then I think that still the average trend is a first parameter to study, or first relationship to look at.